What I'd like to do this afternoon is to discuss an interesting application of the multifractal formalism applied to complex data sets, both 1D and two-dimensional, that are difficult to describe using conventional techniques. So I'll start out by providing a brief primer on what a multifractal process is and the role of wavelets in characterizing the scaling properties of that process. From there, I'll examine a multifractal decomposition algorithm based on the use of Gaussian mixture models, where the algorithm is validated using simulated data sets consisting of different multifractal regimes. I'll then discuss an application involving the classification of satellite imagery known to contain various degrees of cloud cover. Before I proceed, I'd like to acknowledge a couple other folks that were very responsible for a lot of the research work that we did at MITRE on this. One is Damon Frezza, another is David Slater, and the third person is James Thompson, all from MITRE. Okay, so many spatial and temporal data sets exhibit singularities or chaotic dynamics that are difficult to describe using conventional techniques. So these data sets exhibit self-similar or scale-invariant properties best described as fractals or multifractals. So there are a number of different examples of multifractal data sets that occur in nature and also are engineered. And I'll discuss a couple of these in the next slide. However, for many problems that we're interested in, the intent is really to extract statistically relevant information on how a process or system changes over time or space. So for example, in a fluid, the transition from laminar to turbulent flow, the onset of cardiac arrest, or financial volatility in the stock markets. All of these can be described using fractal or multifractal techniques. So many of the examples shown here are sort of self-evident, such as the study of turbulence, geophysical events, cardiac anomalies, and even tissue calcification. In fact, a lot of work that really spearheaded the initial interest in multifractals was really in the area of turbulence by folks such as Kolmogorov and later extended by Frisch that examined the scaling properties of fluids at very high Reynolds numbers. So that's really the boundary between laminar and turbulent flow. There are also more subtle applications of this process, including detecting art forgeries, believe it or not, by analyzing brushstroke patterns, deep fakes in both photographic images and video, and textual analysis of word patterning. For example, researchers at Poland's Institute of Nuclear Physics found complex fractal patterning of sentences in literature, particularly in James Joyce's Finnegan's Wake, which resemble multifractal patterns shown in nature. So there are some very interesting applications of this approach across many diverse kinds of fields. So the basic problem we're looking at is that changes in the fundamental dynamics or spatial composition of a process can be manifest as different multifractal processes. So if there's an origin story to all this, it really begins with Mandelbrot. Okay, these multifractal measures or multifractals proposed by Mandelbrot back in '72 are used to describe the fact that the distribution of physical or other quantities are self-similar across many different scales in a geometric support. So what do we mean by self-similar? Well, we mean they show the same geometric or statistical properties at many different scales. In the example shown to the right is really a very interesting quantum interference pattern that's generated by a group of electrons in a metal. And if you analyze each of the color patterns, they each have their own multifractal characteristics. This was first shown by Philip Anderson, who introduced the concept of Anderson localization back in the 50s. It occurs when quantum interference leads to the complete suppression of electronic transport in a disordered system. So electrons become trapped in a localized state, preventing them from conducting electricity. So they're sort of immobile, but they take on fractal or multifractal dimensions associated with it. So this is a very interesting case in the quantum world where this occurs. So as I mentioned, Mendelbrot described multifractals really as a union of an infinite number of monofractals. So the idea that we had was, well, that suggests that a data set could potentially be decomposed into different multifractal regimes or combined to create a new multifractal. So what we developed here is a new algorithm that explores this possibility using multifractals based on Gaussian mixtures. So instead of having data sets that contain just one multifractal process, you can have multifractal processes occurring at different time scales or spatial scales. And the idea is, can you actually separate out those multifractal processes in a nice way? And the answer is most of the time, indeed, you can. So we had developed this algorithm that allow you to do a lot of this stuff, particularly for image decomposition purposes. All right, some basic background here. A lot of this may be old news to you, but what I'm doing is actually putting this in for completeness. By multifractal, particularly for stochastic processes, x of t on some support t, it's said to be multifractal if the expected value of the magnitude of its increment, which is x of t plus s minus x of t raised to the qth power, satisfies some scaling law as s becomes small. So the smaller and smaller this increment becomes, you have a scaling law that pops out. And it's of the form s to the tau of q plus 1 in one dimension. If I have multiple dimensions like 2, I change 1 to d, where d is the dimensionality of the space that this multifractal is embedded in. E, of course, is the expectation operator. Tau of q is referred to as scaling exponent. And we have a couple of formal mathematical conditions that have to be satisfied. The process has to have stationary increments. T is an open interval on R. The domain of the interval 0t is contained in T for some positive finite t. And the coefficients B of q and the scaling exponents tau q are functions of the moment parameter q, where q is on some open interval containing the interval 0, 1. So that is the formal definition of a multifractal. What people typically look at, however, is what's referred to as the multifractal spectrum, D of H. And that quantifies the global and local variations in the regularity of a stochastic process as measured by a regularity exponent H, known as the Holder exponent. So think of it this way, embedded within the notion of multifractality is local regularity, or the degree of continuity of a function at a point characterized by its Holder exponent H. So how is multifractality and local regularity related? Well, they're related by what's referred to as the Legendre transform, which links the Holder exponent and the scaling exponent to the multifractal spectrum. So basically, the spectrum describes the degree of smoothness in the data. So as an aside, this Legendre transform is determined, if you're interested, using large deviation theory techniques and the method of steepest descent. You can actually get that quantity shown at the bottom of the slide, where D of H is the infimum over the model order Q of QH minus the scaling exponent tau of Q. That's the formal definition of a multifractal spectrum. As an interesting side note, the spectrum is also related to what's referred to as the Hausdorff dimension. And the Hausdorff dimension is a real bear to compute, okay, except for very simple objects. It's the dimension of the set of points T for which h of T equals h. So think about looking at the degree of smoothness of a process, and it has a range, a continuous range of h of T values, okay? For each h of T equals h, I have a set of points that define a set that satisfies that relationship h of T equals h. If I look at the dimensionality of that set, it doesn't have to be dimension 1 or 2, it can be a fractal dimension. And that's the whole point, that these sets are referred to as isoholder sets, and they tend to be fractal in nature. So if I look at the Hausdorff dimension swept across all these values of the Holder exponent h, I sweep out basically what's referred to as the multifractal spectrum. So there's an intricate link between the scaling exponent tau q and the multifractal spectrum, which is really nice because now you can treat very complex data sets. You can actually break them down and look at their properties in terms of their smoothness or continuity. So let's back up and let's recap this in a little more qualitative form before I move on to the actual algorithm. So a multifractal process is a generalization of a fractal process. So only a single scaling exponent, which is the fractal dimension, is needed for a fractal process. And a continuous spectrum of scaling exponents is needed for a multifractal process. So for example, the scaling exponent for a fractal process is just a linear function of the statistical model order, which is shown by that blue curve there. It's just a linear curve, okay? It's the same regardless of the moment order. So the slope of that scaling function is a constant. However, for a multifractal process, you can have different degrees occurring depending upon what the model order is. So the scaling exponent for a multifractal process is typically a nonlinear function of that order. Now you can map it over to the right-hand side and say, well, another way of characterizing a multifractal process would be through the multifractal spectrum or singularity spectrum. So as I mentioned on the previous slide, it can be computed directly from the data by computing the Hausdorff dimension, or the spectrum can be computed from the scaling exponents using the Legendre transform. So the way I think about it, this is similar to the way that the autocorrelation and power spectrum are related by the Fourier transform. All right, the duality relationship between the scaling exponent and the multifractal spectrum now occurs through the Legendre transform. So there's a nice relationship that binds the two together. Okay, so that's an interesting way of looking at it. Intuitively, we would expect wavelets to be an ideal approach for estimating the scaling properties of a multifractal process, and indeed they are. So this brief introduction in no way is news for many of you, but again, I've included it for completeness. So we look at a wavelet function psi of t on L2 of R, and we look at the function psi of j k of t to be of this form here, and that creates an orthonormal basis. So the system of functions then is said to constitute an orthonormal wavelet basis. So a function in L2 then can be written formally as f of t is the sum of the wavelet coefficients d of j and k, where j is the scale, k is the translation, times psi of j k of t, where the wavelet coefficients then look like this. D of j k is given by that integral expression. Now there's an additional 2 to the minus j over 2, which you might be curious about, that pre-multiplies the integral. That's due to the fact that the multifractal community treats everything in terms of L1 norms instead of L2 norms, so there's an additional factor to the minus J over 2 that pops up there. But other than that, it's the same thing. So the statistical moments then of order Q can be estimated from what's referred to as the structure function. So basically what you do is you take the wavelet coefficients, D, J, K, take its magnitude, raise it to the qth power or moment, and then average over all the translations K that comprise a given scale J. And that creates basically the structure function S of J, and Q, remember, is the moment order here. So if the process is multifractal then you can show that the scaling function S of J K also assumes a nice scaling relationship similar to what I had shown on a previous slide for the multifractal process. It's proportional to 2 to the J times the quantity tau of Q plus 1, where tau of Q is the scaling exponent. And that relationship holds true as scale becomes smaller and smaller, in this case, as J goes to minus infinity. Well, that's all well and good. However, there are two important issues associated with the use of wavelets. One, as it turns out that the structure function is generally not independent of the chosen wavelet basis. That means I can get slightly different results depending upon what wavelet basis I choose. And secondly, there's the Nettleson issue or problem of what's referred to as oscillating singularities. These are like chirp patterns that occur in the data, and it leads the wavelet coefficient, well, using these wavelet coefficients then lead to results that differ from what they should be for a multifractal process. So there's an issue associated with that. So there were many proposed solutions over the years to this problem, including, you may be aware of Malot's wavelet transform modulus maximum property that produces a skeleton of scale and time partitions. However, it was shown that even though this works, it's very computationally expensive. So Jaffard et al. Back in 2006 came up with a much simpler approach referred to as wavelet leaders. So a brief description of the approach is shown here, and I'm not going to dwell on it. But wavelet leaders are hierarchical quantities that are monotonically increasing with scale J. So for a set of wavelet coefficients, D of J of K, the wavelet leader is formed by looking at the supremum or max of D of J K in what's referred to as the 3-dyadic neighborhood, 3 lambda JK around K for all finer scales. Now that may sound mind-boggling, but if you look at the figure to the right, it's very simple. If you focus on a given scale and a given translation, say D of 3, and you ask yourself, what is the wavelet leader associated with a scale 3 translation 3, that shaded area shows what it is. Basically, what I look at all scales finer than 2 to the J, and I look to the left and look to the right. So I go 1 down in translation, 1 above in translation, and I look at all of those numbers, and I look at the supremum of all those numbers, and that forms what's referred to as the wavelet scale, wavelet leader. So the actual formula is shown at the bottom, that L of JK is just a supremum over that neighborhood of the magnitude of these wavelet coefficients within that neighborhood. And it turns out that the wavelet leader has some very interesting properties, and it mimics basically the multifractal behavior that we expect in these complex data sets. And it also gets around the problem of these oscillating singularities. It can handle those. So in practice, in the multifractal community, they use almost exclusively now the concept of wavelet leaders to do a lot of their processing work. So using the wavelet leaders, if the process is multifractal, then it satisfies basically the same scaling properties that we had before. So if you take the expected value of wavelet liters raised to the cube power, it scales as 2 to the j c of q, where c of q is tau q plus 1 in one dimension. Change 1 to d, the dimensionality of the embedded space, if you're dealing with d dimensions, as j goes to minus infinity. Okay, well, an interesting thing along the way is because of the form of these expressions, Casting and Delors introduced the idea of using a polynomial expansion to describe the scaling function. So this has really greatly simplified the characterization of multifractal processes in terms of log cumulants. So if you harken back to the analogy of log cumulants, I can take that expected value, L raised to Q power, take the log of that, and I could very simply write that as the log of the expected value of e to the Q log of the wavelet liters. And lo and behold, that expression is basically a log cumulant that people use in probability theory. And we all know that that has a series expansion of the form C sub jp q to the p, or p factorial. So these are the log cumulants. So it turns out now that if I go back to that expression up above at the top of the slide and take the log of that, I can write that as the log of f of q plus the log of 2 to the j c of q, and I expand that in a series representation as well. So now I have a formal representation of all the log cumulants in terms of these coefficients b of q and c of p. They uniquely define now the multifractal process, but it's a very simplified way of encoding all that information in terms of those coefficients. So it could be shown that C of 1 is a location where the multifractal spectrum is a maximum, and the magnitude of C of 2 is proportional to the width of the multifractal spectrum. You can also show that values for which C sub 2 is less than 0 are also representative of a multifractal process. So what's nice about this is that given C1, C2, and any higher order values, we can uniquely characterize what the multifractal spectrum is without literally having to draw what that spectrum looks like. It's all encoded in those coefficients. And that's going to be crucial for this algorithm that I'm going to describe. Oh, okay, so we're ready to outline the problem. There are two assumptions involved in this. One is that the log wavelet liters of any single multifractal process can be well approximated by a normal distribution with mean mu sub j and standard deviation sigma sub j at each scale. Now, it turns out that normality is sort of a surprising property that comes out of wavelet liters. It's been explored extensively by folks such as Combrexell and Wendt, as well as by us as well. Okay, and there is a very nice approximate normality relation associated with this, which actually leads us to think that it's possible then to expand these multifractal processes in terms of these Gaussian mixtures. And assumption two is if more than one multifractal is present in data, then each one of these L sub n of jk are normally distributed, but now with different means, mu sub jm and standard deviation sigma sub jm. Okay, so the algorithm then is based on the notion that a multimodal, multifractal process can be expanded in terms of weighted Gaussian mixtures, okay, where the corresponding means and variances are related by the log cumulant coefficients. So we can then write the mixture probability density, P of L, conditioned on a set of parameters theta, as basically being a sum of a number of Gaussian mixtures, where pi sub jm are the individual weights, probability weights associated with each mixture, and N is shorthand for the corresponding Gaussian probability density functions with means mu and variances sigma, okay? So here's then the connection between the first two moments and the log cumulant coefficients. The individual means and standard deviations can be expressed in terms of those log cumulant expansions that I had just shown you on the previous slide. Mu Jm is B1m plus C1m log to the J, and the variance sigma sub Jm squared is given by a set of coefficients B2 and C2, okay? We define the parameter matrix theta as being theta 1 through theta m, that vector, where theta m is a collection of those coefficients for each of the Gaussian modes, B1m, C1m, B2m, and C2m, okay? Now comes the big assumption. If L and Jk are independent samples, both in scale J and translation K, then we can write that probability density function in terms of that double product. Now, it turns out that independence with respect to a translation K for a given scale J is not guaranteed to be true, okay? And it's very easy to show, in fact, that it is not true, although it's partially true if you look at different scales, okay? Such an assumption is referred to as the naive Bayes assumption because we're making the assumption that each of the individual translations that compose a given wavelet scale are statistically independent, when in fact they're not. But we assume for the moment that they are independent. So it turns out that under certain restrictions, this assumption indeed is valid, and it turns out to be related to the degree of separability between these multifractal processes. And if we have time toward the end, I can actually show you some of the math that sort of led us to those individual observations. So to determine the parameters theta, being good signal processing people, to estimate those parameters, we'll look at maximizing the log likelihood function. And the log likelihood function we have, remember, as the sum of those weighted normals. And we look at the log of P of L conditioned on those parameters theta. However, this is a non-trivial exercise because it turns out that when we set the gradient equal to 0, it leads to a coupled set of nonlinear expressions that are extremely difficult to disentangle. So what we then do is employ what's referred to as the expectation maximization approach. That's a much simpler decomposition based on an iterative framework. So the whole idea behind the EM approach is to introduce one or more hidden variables that are used to decouple the problem into separate components. So in this case, we choose the hidden random variable Z sub JMK, which allows each Gaussian mixture to be decoupled and estimated separately. As a result, the function Q, which is shown below, can be factored in nice form. So what it allows you to do is to treat each set of Gaussian mixtures separately and estimate their means and variances separately without having them be entangled with all the other means and variances associated with the other Gaussian modes. So the likelihood ratio that we're trying to maximize leads to analogous expression in terms of the Q of theta and theta prime. So the idea then in the EM approach is to estimate, come up with an initial value of the parameter theta prime. Then estimate what the probability of Z condition on L and theta prime is. Perform the integration, come up with Q, and then choose the value theta that maximizes Q. That now becomes theta prime, and you iterate through the loop, okay? It turns out that probability density function, P of Z, condition on L and theta prime, can be determined fairly easily using Bayes' theorem. So it's a very closed system that once you actually determine this, you iterate to find what the solution is. But the iteration is a lot more simple in this case because I have this decoupling that occurs. I don't have to worry about treating this huge vector of parameters that I have to estimate. I can estimate these parameters individually, and that's the whole idea. So it turns out that this factorization actually leads to a Q that can be factored in terms of the individual Gaussian components Q sub m. So each of the individual, and I won't belabor the point, can be written as QM1 and QM2, and they're given in terms of weighted values. The WJMKs are referred to as the preferential weights. And if you look at it carefully, they're basically a weighted norm of each of the Gaussian probability density functions for a given mean and a given standard deviation value. So they're like probabilities in a sense, and they basically weight the probability of occurrence of a certain node in the sample data that you have. And this is referred to in the literature as the expectation step, where you're able to do this decomposition. And the mixture probabilities that are referred to, the pi JMs, can be determined by maximizing QM1, subject to basically the condition that all the probabilities have to add up to 1. So basically, it's a Lagrange multiplier constraint. You solve that problem, and out pops basically the mixture probabilities, pi sub jm, and then you plug it back in there. So now the second term, that Q sub m of 2 term, can be written in terms of this expansion here. And it's not a very difficult term because of, again, because of the decoupling that occurs. So you note the simplicity of the expression. Each one is, there's no coupling between terms, so that the means and the variances now are uniquely associated with each of the modes. So I have the mu sub jm and the sigma jm. So there's a decoupling that occurs. Noting that u sub jm, remember, is a function of these log cumulative coefficients that I talked about a couple minutes ago, and so is sigma sub jm. I can actually solve that algebraic equation for B1, C1, B2, and C2, and I get an expression that looks something like this. B1m, C1m equals A inverse B. It's a 2 by 2 matrix, and B is a 2 by 1 vector, and I can get that in closed form. The issue is that I still have to estimate the variance sigma sub jm squared. Well, if you look at the next slide and rewrite that expression a little differently, that's the expression I'm dealing with here. But I realized that sigma sub jm squared, remember, is related to those log cumulative coefficients. Remember the B2m's and the C2m's. So there's coupling between the scales of this multifractal process when I do this wavelet decomposition, and I have to take that into account. So I can basically minimize that quantity to find out what those coefficients are, but I have 2 constraints that I have to subject to. That one, I'm only interested in multifractal processes. So I have to guarantee that C2m is less than 0, and I want all the variances of these Gaussian modes to be at least greater than 0. Okay, so that the condition there would have to be that B2m plus C2m log 2j has to be greater than 0. So the first constraint imposes a multifractal assumption, while the second constraint guarantees that the variances are greater than 0. So this is a classical nonlinear programming problem. that can be solved numerically using what's referred to as the Koresh-Kuhn-Tucker conditions in numerical analysis, which is like a Lagrange multiplier, but now instead of having a strict equality for the Lagrange multiplier, you have inequality constraints. You can solve that, and it becomes a nonlinear programming problem. There are a lot of different algorithms out there, open source, that allow you to do this very quickly. So given then that I can compute the B2Ms and C2Ms, I'm done, because now I have estimates of B1M, C1M, B2M, and C2M. I can plug it in and voila, I can compute what the scaling exponents are for each of the modes. I can also compute the multifractal spectrum then for each of the two modes. Okay, so it's a very slick way using the expectation maximization algorithm of providing that coupling mechanism. So the next slide is sort of busy, but let me just quickly walk you through it. The figure to the right is just a multifractal Gaussian mixture algorithm that's been implemented. Okay, so that's sort of the flow chart for how that algorithm is implemented. The actual Blue Jay image that's shown in the center of the slide actually started out as a black and white photograph that was digitized and decomposed using a 2D Dubussy 3 wavelet. We assumed 3 modes, and the histograms of the 3 Gaussian mixtures relative to the raw wavelet-based data at different scales are shown to the left. So if you look at the histogram fit at different scales, we're assuming that we have 3 modes. What's shown in yellow are basically the raw histograms that are decomposed using the wavelet decomposition algorithm at finer and coarser scales, and the different solid curves are the fits to those. So when you have 3 modes, the fit is very good. After you look at the weighted fit to that, the dotted curve is actually fit to the experimental histograms, starting out at finer scale to coarser scales. Okay, the reconstructed scaling exponents and the multifractal spectrum then are shown to the right. So what's shown in the middle there to the left is the scaling exponent as a function of the model order. And in this case, you can see that we have 2 multifractals that are occurring because of the nonlinearity in the scaling exponent tau q, and we have a straight line, which denotes that we have a fractal. Another way of thinking about that is map that into the multifractal spectrum, where we look at the spectrum as a function of the Holder exponent. So this is really the dimensionality of these iso Holder sets as a function of the smoothness parameter Holder exponent h. And you can see there are 2 apparent multifractal processes shown in red and blue, and there's a little dot that shows that, okay, I have just a fractal process that has no width because its multifractal width is 0. It's just a fractal. And if you look at the image, this is sort of the color coding of the bird, and that's generated from the preferential weights that I showed you. So it's a pixel by pixel mapping. Remember, those preferential weights actually assign basically pixels based on what mode, multifractal mode it thinks it's in. So what we do is we map basically those preferential weights, which is a 2D matrix, right onto the image itself and color-coded based upon the multifractal properties. In this case, we assume we had 3 modes, which were red, blue, and green, and these show up then in the picture of the Blue Jay. So basically what it's saying is the bird itself, its feathers, are basically fractal in nature. It has a fractal dimension, but the background, including the tree limbs and stuff like that, where light scatters off, is far more complex and is best represented as a multifractal process. So that you see in the background image, there's a lot of red and there's a lot of blue, denoting that it has a multifractal characteristic. but the bird itself and the actual scattering off the bird feathers for the camera tends to be more fractal oriented than multifractal in nature. So this is a very simple example, and I'll go into more detail in a moment about the actual validation of this algorithm on actual multifractal data. But this sort of gives you an idea of how you can take fairly complex images and sort of decompose them to understand what their multifractal properties actually look like. Before I do that, there are a couple points I just want to make, is that algorithm initialization is an important step in the process. You have to start somewhere. We don't know how many modes there may exist in an image, whether it's 1D time series signal or 2D image. We don't know how many modes may exist. And we don't know what the initial values are for the individual means and variances associated with each of these modes. So we need an initial estimate of the modal order M, or the number of Gaussian mixtures, and the separate means and variances associated with each of those Gaussian mixtures. So it turns out that M, the modes, is determined using what's referred to as the Bayes information criteria, or BIC. So for those not familiar with the Bayes information criteria, it's based in part on the likelihood function L that I know, and it's closely related to other things that you may be familiar with called the Akaike criteria, if you've ever done any work on like 1D autoregressive processes. Okay, so BIC then could be written as K log N minus 2L, where K is the number of parameters, N are the number of data points, and L is the likelihood ratio. Okay, so we can estimate M that way. And initializing the means and the variances require a more nuanced procedure, which is sort of outlined in the block diagram shown to the right in this slide, okay? Initially, the parameters are initialized. We cheated a bit because there are nice packages that we could use. One is the scikit-learn package, which is a Python machine learning package that could be used. But there were some issues with that because we had an issue of actually locking into local minima using those kind of algorithms. So what we did is we augmented basically the selection of our initial vectors, mu naught, and our variances using coarse data clustering methods, such as quantile partitioning, mediums, and k-mean cluster analysis approaches, together with this scikit-learn package. So we came up with a very robust procedure then of being able to initialize this algorithm. Okay, in terms of numerical tests, we have to start out and say, okay, how well does this algorithm work? Excuse me, because we made a number of initial assumptions way back when. So to test the multifractal Gaussian mixture model algorithm, we require data sets that consist of different multifractal regimes. So the 2D data sets that we used were generated over a range of these C1 and C2 values. Remember, C1 and C2 gives us an idea of where the placement of the maximum of the multifractal spectrum is, and C2 gives us an estimate of the width of that multifractal spectrum. So we can generate all different varieties of multifractal spectrum based on this, and we use the multifractal random walk model approach as outlined by Garry. And if you're interested, I'll just spend a minute as an aside. The process is really generated by computing the 2D fractional Brownian motion increments. So if you look at the increments, they turn out to be fractional Gaussian noise. And that fractional Gaussian noise has an associated covariance matrix associated with it. You multiply that FGN by another quantity, which is the 2D correlated Gaussian field, using Garry's covariance function. So you combine the two together, okay, you integrate the result, and what you get is what's referred to as a multifractal random walk. Well, that seems fairly complex, except for one thing, is that all the covariance matrices tend to be toplets. And toplets matrices have some very interesting properties, and then I can embed them in a larger circulant matrix. And then if I embed it in a circular matrix, I can compute all the corresponding eigenvalues and eigenvectors directly by a 2D FFT operation. Okay, so I can do it very efficiently and very quickly. Okay, so for the experiment, there were 20 unique multifractals. We chose 4 C1s and 5 C2 values for a total of 20 multifractals. And each of the multifractals used were used for both foreground and background images. So think about it as we had 20 and then the remaining 19 background, and we flip it. So 20 times 19, we have 380 different image sets that we're looking at. So what you see on the right is actually an output of one of those image sets, which looks like a lunar landscape. There are actually 2 embedded multifractal processes in there, which are difficult to see. Okay, but there are 2. Okay, and the interesting thing is, in order to get this, is a long and tortured story that I won't get into, but in order to generate that image, we literally had to include the multifractal components through a wavelet-based reconstruction. So we started out at the finest scale and actually built it up or reconstructed it from the multifractal coefficients to get this image that you show here. So this is a true 2D multifractal spectrum. So there are 3 test criteria that we looked at. One is the correct number of multifractal regimes, i.e. the model order, the correct estimate of the multifractal properties, and then the correct labeling of each of the pixels. So BIC, this Bayesian information criteria, was used to assess the correct number of multifractal regimes. So since it went through an extensive simulation, which shown on the upper right are the number of multifractal regimes, and you can see that in terms of the probabilistic outcome, the most likely choice in this case is that these images that we looked at had 2 multifractal components. Well, they better be, because that's the way the data was set up, but the algorithm didn't know that. It basically started out estimating different model orders and arrived at a fairly high probability of having 2 multifractal components. In order to estimate the correct estimate of multifractal properties, we used the root mean squared error to assess the correct estimate of those properties. And if you look at that, the mean squared error is basically just the average over model order of these the estimated versus true scaling exponents tau of q. Okay, so you see the sum of the quantity C1 minus C1 hat, that's the estimate. C2 hat is the estimate of C2. And we form that sum and square it and then average, and that gives you the mean squared error for the scaling exponents. And since we're looking at both the foreground and background, we include that as well, take the square root and get the root mean squared error. So that's what we get. What's shown on the lower right then is a depiction of what that RMS error is as a function of delta C1, which is the difference in the absolute value of C1 values between the foreground, FG, and the background, BG. And that's also parameterized in terms of C2 values as well. So what you see is something interesting occurring here, that as C1 increases, delta C1 increases, the average RMS error actually decreases, and it decreases very quickly. Also, we noticed that for smaller delta C2 values, the average RMS error is smaller than for larger delta C2 values. You may ask, what's happening here? Well, what's happening is a simple result that as C1 governs basically the maximum of these multifractal spectra. So as these spectra slide out and delta C1 becomes larger and larger, there's a greater degree of separation, which means there's less confusion in choosing this multifractal process over this multifractal process. Additionally, delta C2, remember, is related to the magnitude or width of each of the multifractal spectra. So if I collapse down the width of these guys, what I'm doing is actually increasing the separability again of these two multifractal processes. So there's a very interesting linkage between delta C1 and delta C2. Partially it's through the process itself, and as I'll show you in a little while, part of it has to do with the naive Bayes assumption that we employed up front, saying that the translations, the wavelet translations, were actually statistically independent. That's also an issue here as well, which I'll discuss in a little while. But this sort of gives you a rundown of what's going on there. And then the third part is the correct labeling. So here we're interested in the typical quantities, like what's the true positive, what's the false negative probability, and what's the false positive probability. And again, we get the same results that I showed you before. If you look at P of H1, condition on H1, basically we're looking at true positive, saying that we actually have a multifractal process this form, when indeed we do. It turns out that for large separations, delta C1, between multifractal processes, the probabilities are quite high. And they decrease as delta C2 increases, because now you're increasing the width of these multifractal processes, and you have more and more overlap that's occurring between these two. The same is true of P of H1 condition on H0 and P of H0 condition on H1. And I won't run through the details of how each of those probabilities are computed, but if you're interested later on, you can go back. We basically just sort of threshold the results and then look at the number of pixels for which these preferential weights are greater than some given threshold. So we're looking at the cardinality of the set, counting up the number of pixels and saying, okay, how many pixels have been identified in this part of the image over the total foreground image, or the total composition or number of points, say in the foreground image. And we could do the same thing in the background image as well. And that gives us the three probabilities: true, false, negative, and false positive. So a couple of takeaways from this experiment is that the algorithm can correctly determine the number of mixture components around 83% for design points. And the average RMS error in the scaling functions was somewhere around 0.83. And the algorithm allocated each pixel to the correct multifractal regime for about 70% of the pixels. Some of the observations, though, is that the algorithm, as I mentioned, improves as delta C1 increases. Algorithm performance generally degrades as delta C2 increases, because you're increasing the width, as shown in the picture to the right, of these multifractal processes. So that creates more overlap between the two processes. Although there tends to be a very complex interplay between delta C1 and C2, what I said is qualitatively true. And this really has to do with the degree of separability between the two multifractal processes. Larger delta C1 and smaller delta C2 increase the separability. And it turns out that this is also consistent with the naive Bayes assumption that we invoked at the start. Okay, I'd now like to shift focus and examine an interesting application of the algorithm to cloud cover classification using satellite imagery. We didn't expect this algorithm to work at all, because it wasn't designed for cloud patterns or for detecting clouds relative to different landscapes and backgrounds. But we decided that since we had the algorithm, we're going to give it a test. And to our surprise, it worked quite well. A lot of studies in literature, in fact, a lot of the work at USGS indicated that multifractals are ideal for modeling various meteorological features such as clouds, rain, and turbulence. And these processes have also been used to detect areas of different textures in satellite imagery. So here we look at a possible application of our algorithm to segment different satellite imagery known to contain varying degrees of cloud cover. So we took an open source data set, which is the Landsat 8 cloud cover assessment validation data, and attempted to demonstrate the utility of this algorithm for segmentation. Now, I have to say that this is not new in the community. In fact, there are a lot of folks that have developed segmentation, cloud segmentation algorithms. All we're trying to do is to take the algorithm that we're using for other purposes and see if it could be applied to this problem as well. So a lot of these cloud detection algorithms already exist. So we have pre-validated data sets that are freely available. So a lot of these pre-validated data sets we use actually to validate our own Gaussian mixture model. So the Landsat 8 data was taken from the pre-collection operational land imager thermal infrared sensor. And as I mentioned, these are all open data sets. There are 8 bands that range from roughly half a micron up to 1.38 micrometers at 30-meter resolution. And it has 8 different bands. Band 1 is the lower end of the visible blue spectrum that goes all the way up to band 5 through 8, which we used for this analysis. So that extends from near infrared to panchromatic. All panchromatic means is that it's sensitive to all visible colors. So what you see basically is a band 5 image of a snowscape with 55% cloud cover shown in the upper right. And the cloud masks, which were done by experts at USGS using their own algorithms, actually delineated what were clear areas versus thin cloud cover versus heavier cloud cover shown there. Okay, so we have cloud masks and we have all the image data. And these masks were manually generated and validated by experts. Okay, so we analyzed 96 scenes in 4 bands, band B5 through band B8. So there are 96 times 4 or 384 images total. And there was 1 cloud mask per scene with intensity values which range from 0 to 255. And the cloud mass, the centroid of the cloud mass data you can see on this little table with values 0 to 25 that delineate the various degrees of cloud cover that you have. So we tested the number of components selected first, and then forced the algorithm to look for the exact number of components. And we then computed the output of the Gaussian mixture weights at the finest scale, and then normalized the results. Am I running out of time, or can I go another 5 minutes?
Yes, a couple more minutes.
Okay, all right. I tend to be a little long-winded, I apologize. We then construct a score matrix, okay? And we map them into various categories. In the score matrix, then the preferential rates are then converted into a binary map. And that binary map is then compared to the original map that the experts came up with. So very quickly, this is sort of a selection of the proportion of correct predictions, the proportion of false positive predictions, and the proportion of false negative predictions. So what you can see here is something very interesting, is that the algorithm performs best at isolating the cloud shadow category and tends to do better over barren or snow landscapes, and its lowest value appears in the clear category, okay? And the same is true for the false positive and false negatives. This is a qualitative example where the algorithm did very well, which is clear cloud, and it didn't do so well for thin cloud, thick cloud predictions. So quickly, some takeaways. Even though we didn't think the algorithm would work on data such as this, it performed moderately well at some specific tasks. It correctly allocated 71% of the pixels in the Landsat 8 image. Its best performance was at isolating cloud shadows, 90%, and tended to do better over barren or snow landscapes. Now, what's interesting is that the number of components that our algorithm came up with were a lot larger than the number of components the experts came up with in their cloud mass. And that was primarily due to the number of different landscapes and different textures of the way the clouds were grouped into one category. And it turned out that the clear category did present challenges because the algorithm did not see this as a single category comprising one multifractal. Because the experts looked at that and said, yeah, there are different textures, but I'm going to classify this as just one landscape. Our algorithm went in there and actually parsed it into multiple different types of landscapes. For our analysis on validation, we didn't take that into account, but the thought was that this algorithm could then potentially be used to actually dig a little deeper into the actual formation of these different cloud patterns. So I'll quit here. This is the summary slide. A lot of this you already know about. It turns out that the algorithm is well suited for unsupervised semi-automated data segmentation. We tested the algorithm on simulated data and it performed quite well. In data we didn't think it would do so well on, which is cloud masking, cloud pattern imagery, it surprised us in doing quite well. I have to mention, being a good mathematician or scientist, there are improvements that are anticipated here. First thing I want to do is remove the naive Bayes assumption, which was the independence assumption. But after giving it a lot of thought, it turns out that's not going to be as hard as I thought, because we can reformulate the problem as a joint Gaussian mixture model. Instead of having marginal Gaussian mixtures, we now have multi-dimensional Gaussian mixtures with known covariance matrices associated with it, parameterized in terms of those log cumulant coefficients. The interesting thing is, though, that's a wicked problem to decompose, but it turns out if your data set is large enough, a nice basis for representing this is the Fourier basis, and it's referred to as the Whittle approximation. If you have a Gaussian multidimensional data where the dimensionality of that data is very large, a good approximation is called the Whittle approximation, which allows you to decompose that problem into components where the eigenvectors associated with those covariance matrices are actually the Gaussian kernels, and the eigenvalues are proportional to the actual spectrum at the sampled frequency, spatial frequencies. So if that's the case then, and it appears to be, we can decompose that entire problem into a different basis and then treat it as a naive Bayes problem, except now the representation is in this alternative basis, which is the Fourier basis. But the mathematics should carry over very nicely and allow us to really generalize this approach beyond what we normally thought we could do with the independence assumption that we invoked up front.